learned from yesterday, yes, ma'am, the dark matter density goes up from what we have in lambda CDM without dark radiation. Now, now it becomes a bit subtle. Bear with me. Another thing that's important and pretty well measured is the sound horizon. So the distance that perturbations in the primordial plasma can travel, from 0 to formation of the CMB, essentially recombination. So the physical length is just the integral from Big Bang to recombination of the sound speed, where am I, over time, and we have to take into account the scale factor of the universe. And as the Hubble parameter is scale factor time derivative divided by the scale factor, we can rewrite this into an integral over the scale factor. We have Cs over a squared dA over the Hubble parameter, and then we go from 0 to a recombination. Of course, we don't really start at 0, but it doesn't matter. Here, Cs is the sound speed and the baryon photon plasma. So you see, we've got the Hubble rate here, and if we increase the radiation energy density, we have to increase the dark matter density, which means the Hubble parameter has to increase, and that means this Rs will go down. So yeah, let's just leave it at that. This becomes smaller. That's not a problem per se, because what we really see in the CMB is angular scales. I mean, we are looking at multiple expansion. So what measures the angular size? Let's call it theta s, which is this sound horizon divided by the distance from here to the last scattering surface. Let's call it dA. Where dA is just the distance that light has traveled from formation of the CMB to us. So we integrate there from last scattering, Ls, to today, T0. And in this case, it's like before, but now light. So we've got the speed of light, which is 1, of course, so I can leave that out. And then time over scale factor. And of course, this you can rewrite precise in the same way to have 1 over the Hubble rate down here. And so if we increase the Hubble rate due to the increase of radiation and the matter density, this distance to the last scattering surface also decreases. However, the decrease of dA will be less than the decrease of Rs, because the Hubble rate here, that's inside the distance to the last scattering surface, is at late times dominated by the dark energy density, which we haven't changed yet. Whereas here, this H there is essentially radiation and matter only. Dark energy didn't matter in the early universe. So this H here changed considerably, whereas the H in that integral doesn't change that much. So we can say the A goes down, but not as much as Rs. And that, of course, means here in the angular size of the sound horizon, I increase the numerator and I increase a bit less the denominator. So the angular size goes up. The other way around, sorry. So the numerator decreases and the denominator decreases, but not as much. So this becomes larger relative to the numerator. And so the sound horizon actually decreases. There we are. Now this is not a good thing because the angular science of the sound horizon determines the positions of the peaks in the CMB, in the power spectrum. Big position where they move around, but don't stay constant, which is a bad idea because, of course, these positions are also very well measured. And no, so that's it. Not observed, and consequently, we have to prevent this change from happening. And I kind of already gave away the answer because I said that here this doesn't change so much because at late times H is dominated by the dark energy density, which we haven't changed yet. So, well, let's just increase the dark energy density as well, so that the late time H decreases as much as the early time, or increases as much as the early time Hubble parameter. So want to keep theta as constant by increasing dark energy. So bottom line is, if you add radiation energy density to the universe, you better add a bit of dark matter and dark energy as well, so kind of everything goes up, except baryons and photons.
Excuse me?
Yeah.
Can you compensate the shift of theta by giving some non-zero curvature contribution?
Non-zero what contribution? Curvature. I suppose so.
So depending on the curvature, the position of the angular peak is also shifted, right?
Okay, I don't remember, to be honest, but if that's the case, I suppose you could do that. Well, let's say the standard law is that the best way to compensate this is to add dark energy. So I suspect that adding curvature would be in tension with some other measurements. But it can also be that people just prefer a flat universe, and therefore this is the easiest way out, and that a bit of curvature would be perfectly fine.
Okay, thank you.
Okay. And right, so far essentially we've managed to put in dark radiation without changing anything in the CMB. And yeah, maybe because somebody asked about this yesterday, let me also quickly mention another thing where we don't change anything necessarily yet. That's the matter of anisotropic stress. So. Anisotropic stress means if we have radiation that is not interacting with itself or anything else, it doesn't behave like a perfect fluid. So acting radiation. Of course, that's what neutrinos do. They free stream, so they have this anisotropic stress. And the simplest assumption for dark radiation is that it also doesn't have additional interactions, so it also has an anisotropic stress. And that, again, has an influence on the CMB because free streaming dampens density fluctuations. And essentially, the consequence here is that if we increase dark radiation, that means the higher peaks get dampened. So power in the power spectrum goes down for large but not terribly large L, something like 130. I've read the review I'm going to. And so that's something you can compensate in two ways. Either you just change this assumption of non-interaction, as who asked yesterday, well, was pointed out on Tuesday, or you can change the spectrum of primordial fluctuations. So essentially this means that the anisotropic stress does not necessarily lead to a strong bound on an effect. So let me say here, compensate by changing the amplitude and spectral index of the primordial fluctuations, AS and NS. That's the usual letters, right? I didn't know it, but I think that's it. Or avoid by interactions. Of dark radiation. Good. So just to mention this as well. And then we can finally come to the point where something happens eventually, and that's silk dangling. That's again a suppression of power in the microwave power spectrum, because photons can diffuse and therefore they will smooth out inhomogeneities within their mean free path. So dampened fluctuations with a scale size less than diffusion length RG. Now diffusion is a random walk process, so this is depends on the mean free path between two collisions, so on the cross-section for interactions of photons with electrons, and on the square root of the time the photons have to random walk. Importantly, it's the square root because of this random walk. You don't go linearly because photons don't always go in the same direction. And the time you have is essentially the 1 over the Hubble constant, the age of the universe. So our diffusion length here is essentially 1 over the square root of the Hubble parameter, and I'm ignoring here the scattering cross-section. And so again, that's a parameter we increase because of all the arguments earlier, and also just by the fact that we added radiation. So this diffusion length goes down. So this and this decreases in the presence of dark radiation. RD constant. Yes, exactly. However, again, this is the linear size. What we're interested in CMB analysis is the angular size. So the diffusion angular size theta d is our RD diffusion length divided by the distance to the last scattering surface that we already had earlier, dA. And as we figured out, we have to increase dark radiation, dark matter, dark energy, which means the H in that affects here dA rises essentially linearly, whereas our RT here decreases only by the square root of H. And so as a result, this theta d here has to go down. So, no, again. Sorry. Well, maybe I should just say this is just work it out. So this is something like 1 over root h. This is of course now a very crude estimate here, divided by 1 over h. And so yeah, we have the square root of h in the end, and so theta d goes up. And that means for larger angular sizes, we have photon diffusion and thus silk damping. And that means when we talk about power spectrum, we start at lower L. And so overall, this damping sets in earlier when we go to higher L and becomes more important. So essentially, we can say that we have more silk damping and therefore less power on really high scales of above 1,000 or so for L. And that's kind of conventionally the main lever to set constraints on dark radiation from the CMB. And yeah, let's just put in here the result.
Excuse me?
Yep.
Maybe I missed what does that specific number means in the second line in the right side from above, from the top?
This one?
L larger than 130.
Oh, that's for the anisotrophic stress. For silk damping, it's higher L.
No, I mean the L larger than 130. Why does the number 130 mean something?
It's essentially just the result that you get when you do the fit. So it's not. I don't think there's an immediate estimate for why it has to be that.
Okay. I tried to understand if there is any connection with that number to some physical thing, but you are saying that.
No, it's essentially the free streaming length. I suppose it's similar to the free streaming length of neutrinos and the scales they affect. Does that make sense?
Okay. I'll think about that. Okay.
Yeah, I'm not perfectly sure, but that would be my guess because I think it's the same physical effect.
Okay,
but of course, I mean, that's then again just another way to phrase it because I don't know of an obvious way to calculate the L at which the neutrino set is. I mean, that's you have to work a bit. So
okay, thank you very much.
That's a homework for everybody.
Mm-hmm.
Okay, and then let me cite the result from Planck from the famous last paper on cosmological results. I already have it somewhere. And that's delta N effective is less than 0.29 at 95%. That's usual confidence. So we see nowadays BBN is more sensitive to dark radiation than the CMB because the BBN bound was 0.13 or so, and here we have a factor of 2 worse. I should also add that this is not only Planck observations, but also some baryon acoustic oscillations, large-scale structure observations go in there to break some degeneracies that you otherwise have in the fit. So yeah. If you don't use that, then the bound will be a bit weaker. You can also argue that, okay, in the standard model, N effective can only be larger than 3, so you shouldn't take into account negative delta and F, and then if you just do one-sided statistics, the bound is 0.30. So bottom line is this doesn't matter much if you just look at this number. And I guess what I should also say is that there's also some dependence on BBN here again, because another way to address the silk damping here, or in fact a way to compensate the effect even for silk damping of dark radiation, is to change the cross section of, or not really the cross section, but the mean free path that the photons have while they diffuse, by changing the density of electrons in the plasma. This you can do by changing the number of helium nuclei you have around, because helium has a large binding energy, so it recombines earlier than hydrogen, and by the time the CMB gets formed, helium is already neutral. So if you have more helium, you have fewer electrons, and therefore a larger diffusion length for the photons. And I guess in our case, what we like is to make it smaller again to compensate the effect of silk damping. So we should reduce the helium fraction. And so if you pretend not to know anything about helium, then yeah, you could even avoid this bound or weaken it significantly. But of course, we do know about helium from BBN, and therefore, yeah, you don't have so much freedom there. But it's another reminder that BBN and CMB are intertwined, and although I'm presenting them here as separate subjects, there is always some crosstalk. Yeah, what I should also mention as another caveat is that not everything is perfect in the CMB observations. There's some inconsistencies between high L and low L data. There's an anomaly of the amplitude of CMB lensing, gravitational lensing of the microwave background. And yeah, that could indicate that we have some systematic errors that the good people of Planck have not as well under control as we think. And that could indicate that maybe this bound is a bit too strong. Just in case you'd like to be super cautious, let's say. Yeah, maybe let me connect again here to show you some another little thing I like to present, although it's now maybe more historical than current. No, that's the wrong file, pardon. I closed my presentation before. No, there it is, I think. Fix. Ah. Oh, that's weird. Well, let me try. Somehow my Zoom is not cooperating as much as I'd like it to. Because I was still in full screen mode, probably. Okay, anyway. So, I told you Planck says delta NF is less than 0.3, and there's essentially no indication for dark radiation whatsoever. Now, of course, there are more other people observing the cosmic microwave background, and kind of like 10 years ago, this was sometime 2013, there were quite a lot of measurements that had a pretty high number of effective degrees of freedom. Here 3 or 3 point a little bit is the standard model, and if you look here, there are huge error bars and a bit of scatter, but kind of everybody is observing large values. So that used to be a fairly strong motivation, I think, for considering dark motivation, and maybe you can still view it as an indication that, okay, maybe there's actually something to see here. Because essentially, you asked yesterday, Tuesday, about the motivation for dark radiation. So that's, I think, a part of it, together with the other potential tension in the data. And then, of course, there's the actual really big tension between the CMB and Adam Rees when it comes to measuring the Hubble constant. And so let me address this. So again, in the Planck cosmology paper, the present-day Hubble parameter H0 is fairly small, 67.4 plus minus 0.5 kilometers per second and megaparsec. And then there are the cosmic distance ladder measurements, which essentially make observations today. Of course, it was a few million years ago, but also a million years in cosmology. So I call these the local measurements using Cepheid, supernova, tip of the right giant branch, and the like. You've certainly heard about this. And yeah, just citing the latest Rees et al. Paper. Or kind of the latest, which has the smallest error bars, 21, 12, 04, 5, 10, 10, H0 is 73.04. They start, keep adding significant digits, plus minus 1.04 kilometers per second and megaparsec. And yeah, these numbers are certainly clearly incompatible. That's about a 5 sigma tension by now. Oh, probably you can't see that on the screen anymore. I just wrote 5 sigma there. And yeah, that's also motivation to consider a dark radiation, because we've seen that when we increase the effective number of neutrino species, that increases the radiation energy density and also the matter energy density and the dark energy density. So all energies increase, and that means also the Hubble parameter, including the Hubble parameter today, increases. And so we can nicely bring these measurements into agreement, right? Because of course the Cepheids don't know anything about dark radiation and stuff. So this value will be unaffected, but of course the value we read off from Planck will be a lot larger by having dark radiation, and problem solved. And I mean, to be fair, even the Planck people in their 1807 and so on papers say the tension is somewhat eased, because it turns out you can't go as far to make it really these numbers equal, but you can go down to, I don't know, 2 or maybe 3 sigma. Problem is, this is ignoring another observable we shouldn't be ignoring. So let me show you here. I mean, that's the famous plot by the Planck people themselves. We have here NF, here the standard model, here we've got the Hubble constant, and that's their error ellipse. We essentially, yeah, they are here at 67. They want to go there to 73. Okay, that was an older Rees et al. Paper. And we see that by increasing the number of effective degrees of freedom, we get kind of into the region of Rees et al. So things look good. If only they hadn't included these colored dots here. A lot of people pretend that they are not there and say that, okay, we add the dark radiation in my model so I can solve the Hubble tension. Yeah, the colored dots are there for a reason, because there is another observable which is called sigma 8, and this happens to be also changing when we put dark radiation into the game. Maybe let me quickly note that then. What is sigma 8? That's a difficult question because the precise definition seems to be classified. I couldn't find it, but I didn't look for more than a morning or so. What it is qualitatively is the present day amplitude of matter fluctuations. So let me just say matter fluctuation amplitude. And the 8 is there because we measure those fluctuations on a scale of 8 megaparsecs divided by little h. So scales of size 8 over h megaparsec, where little h is the value of the Hubble constant we have here in the parentheses divided by 100. And yeah, so this is kind of for CMB purposes, it's a derived parameter. It comes out from the fit. And you see here that if you increase NF and effective, here the dots become redder and redder, which means sigma 8 goes up. And why that is, I spent the better part of yesterday trying to find out and couldn't. So if anybody has any insight on this, I'd be interested. So for practical purposes, if you throw your parameters into the CMB fit, then this is what happens. Sigma 8 goes up. So say sigma 8 goes up for an effective increase. That by itself is fine. The CMB fit here is not terribly much worse because of large sigma 8. The problem is that the CMB is not the only thing sensitive to sigma 8. There are also galaxy surveys which measure matter fluctuations pretty much directly via weak lensing. And these galaxy surveys tend to find a value that is smaller than the Planck value already in lambda CDM with no dark radiation. So I'm running out of blackboard space here. Galaxy surveys get sigma 8 from weak gravitational lensing. That means you are not looking at an individual galaxy that gets distorted or multiplied by a strong gravitational lens, but you look at making a statistical analysis of many, many galaxies that get a little bit distorted by lenses in the foreground. So you look at the shape of galaxies and things like that. And this allows you to infer how much matter is there between the galaxies and us. And that allows you to infer the dark matter distribution and thus sigma 8. And and what they find, okay, now another complication, they actually are most sensitive not to sigma 8 directly, but to some funny combination. Most sensitive to the parameter that's called S8, and that's sigma 8 times the square root of omega matter divided by 0.3. Is that right? Right. Okay, and what they find can be compared, of course, with what Planck finds, and they tend to find a low value. smaller value than Planck. This is shown here in a nice compilation in the Snowmore's white paper on cosmological tensions here. That's the archive number. And yeah, so here's sigma 8, and I think the blue band is the CMB. Up here is Planck measurements, and then down there are weak lensing measurements. And again, there's a bit scatter, and not everybody disagrees, but they're all on the low side. To be fair, the most recent measurement by DES, the Dark Energy Survey, is actually higher and could be compatible with Planck. So it's not obvious what the final result is here, because it depends on the collaboration, what you find. But generally, we see some tension between weak lensing measurements and Planck of maybe 2 to 3 sigma, depending on the paper you read. And that's in lambda CDM, that's without dark radiation. Now, if you put in dark radiation, sigma 8 goes up as inferred from the Planck fit. So that's here the sigma 8 that Planck measures. Those weak lensing surveys, again, they don't care about what happens at recombination, they measure later. So their value of sigma 8 will still stay low. So with dark radiation, you essentially, the blue band here moves to the right and everything else stays where it is. So you increase that tension. And that means that dark radiation as and by itself does not make everybody happy, because you make one observable, you reduce one tension, the Hubble tension, but you increase another tension, the sigma 8 or the S8 tension. And look at here. If F goes up, then makes the S8 tension worse.
Planck's plot in the last the Planck one, and the ineffective and sigma 8 is shown. In the Planck's the previous.
These here. Yeah, that's I think these are simply 1 and 2 sigma contours, and I don't know what the dash thing is. Sorry.
I was just asking that this is only by increasing the radiation density, right? They have not increased the matter.
Oh no! This is kind of the whole fit. Just projected onto this plane, but they essentially do everything. I mean, they don't do everything what I do here. They just run CAMP or their analysis software, and in the end, they simply have a fit of everything. In fact, what exactly happens to all the other parameters is a bit hard to find out, because they don't tell that. In particular, if the statement that the matter density goes up is still true when taking into account some measurements related to sigma 8 is unclear to me. But generally, it's just a normal CMB fit that lets everything float. But of course, in this fit, the weak lensing measurements are not included. This is just Planck plus their bioacoustic oscillation things. They need to break degeneracies and maybe a bit of BBN, but no weak lensing. Certainly good point. You have to be aware of what's in the fit, essentially. All right, so bottom line, if you write papers with a model with dark radiation, that's fine, but please do not claim that you solve the Hubble tension while ignoring the S8 tension. One thing that might help here is to use this fact that dark radiation with a finite rest mass is equivalent to hot dark matter, because that means eventual dark radiation becomes like a particle, and so it's more like massive neutrinos. It has some free streaming effects, which decreases because it washes out matter fluctuations. So this tends to decrease sigma 8 again, and yeah, that might be a direction that that helps to address both tensions at the same time. But I don't think anybody claims that you can solve them completely, just so easily, let's say.
Excuse me, can I make a comment?
Sure.
Yeah, I think if you increase some amount of the gradation, you can see that the sigma 8 increases as well from this plot, and that makes this the tension in sigma 8 measured by Planck and measured by the weak gravitational lensing more serious, I mean more tensions, right?
Exactly.
I think the one way out of this is that if there is a particular type of interaction between dark matter and dark radiation, that can modify, that can increase. I mean, in that case, sigma A can decrease while Hubble parameter increase. So we can relax this. I mean, Hubble tension and the sigma 8 problems simultaneously. So for
Right.
that purpose, dark matter and dark radiation scattering is generated by some very light T-channel mediators. So there are some particle physics model for such case, including 3 papers from Yongtang and myself already several years ago. Yeah.
Exactly. That's actually
yeah.
that's actually the direction I wanted to talk about next. But yes, so that's certainly another another direction you can try to go. If you want to get an overview of other things people have tried, you can look into this SNOMAS paper, where kind of the authors cite everything that they have done ever on the subject, and so a lot of models come out. Models are mentioned there. A lot of further models are not mentioned because they are not authors of the SNOMAS white paper. But anyway, before I go on, maybe any other questions or comments regarding the effects of dark radiation part? Okay, then yeah, let me talk a little bit about model building. I'll switch this off. We said we want to computer running, but take this out. Oh, let's see what happens now. I might have kicked myself out of the meeting, but anyway, for a few minutes I'm gonna use the Blackboard again. All right, so in the remaining 15 minutes I still have, let me talk a little bit about aspects of model building for the model builders around us would like to construct stuff, including dark radiation. And well, I'll use this to shamelessly promote 2 of my own papers while mentioning a few others. So the first is a model of self-interacting dark matter that also interacts with dark radiation. So self-interacting dark matter and radiation, where the starting point is dark matter self-interactions. That can address some small problems of lambda CDM that I didn't mention yet. Those related to the formation of small scale structures, dwarf galaxies, essentially. So yeah, So at least some of those small scale problems can be addressed by making dark matter self-interact. What cannot be addressed is the missing satellites problem, which is about simply how many dwarf galaxies we see around the Milky Way. And this can be addressed by making dark matter and dark radiation interact. So, yeah, simply to pick up Byung-Won's comments, this is related to how much fluctuations we have, and so related to sigma 8. So yeah, as I said, let me mention my own paper here. I wrote with Thorsten Ringmann and Jasper Hasenkamp in 2013 for 7, and then there was a paper pretty much at the same time by Dasgupta and Kopp. That's here 7. That looks earlier, but actually they included this only in the version 3, so we were still first. And Byung-Won, don't worry, I'll get to your models in a minute, or one of them at least. So the idea, what we have here is, let me maybe make a little table. We've got dark matter, and let me put in here the mass. This is by default around the TeV scale, but you can also find fits a bit below a GeV, it turned out later. We've got a dark photon and a dark Higgs at the MeV scale, so that's our light mediator of making the dark matter self-interact, and it's a gauge interaction, so we have a dark Higgs to break this gauge group spontaneously, and then the dark radiation is made by a dark neutrino, which is at the electrovolt scale. So this is essentially a off-the-mill sterile neutrino that could be seen in oscillation experiments, except that it's also charged under the star Q1, and therefore it's not strictly speaking sterile. It's just sterile with respect to the standard model, but it does interact with the dark photon, and hence we also have these dark matter, dark radiation interactions. Now, as I'm mainly talking about dark radiation, I thought I'd mention quickly what you get out, or how you calculate delta N effective in models of this kind. Because it's, kind of the default assumption, especially if you talk standard neutrinos, is if you simply add one species, delta NF is 1 because it's just one neutrino more. However, that assumes that this new neutrino and the standard model neutrinos have the same temperature. And if you manage to keep them a bit far apart, not thermally, not in perfect thermal equilibrium, or both equilibrized, then you can ensure that the dark stuff actually is colder than the standard model neutrinos, and that means you've got a factor of temperature ratio to the 4th power that suppresses delta N effective and moves you in the right direction. Obviously, delta NF equals to 1 is completely excluded these days. And yeah, let me quickly write down what I have there. So we have a thermal contact between the dark sector and the standard model sector via the dark Higgs or the Higgs portal, because this dark Higgs can of course couple to the standard model Higgs. So let's say that means that the temperature of the dark sector is equal to the standard model temperature. Let me particularly talk about the neutrinos, which of course are at higher temperature, have the same temperature as the photons, or T larger than some decoupling temperature of the dark sector. And let's assume this is a really high temperature, like hundreds of GeV or TeV or so. That means that once we drop below this temperature, the two sectors evolve independently of each other. There's plenty of particles in the Standard Model that go non-relativistic and heat the photons. So the Standard Model thermal bath is heated, the dark bath isn't, and therefore this Tx here is simply smaller than the neutrino temperature. And yeah, by entropy conservation, you find that delta N effective at some temperature T, let's keep this open for the time being, is the temperature of the dark neutrinos divided by the neutrinos to the fourth power. No prefactors because it's still a fermion, so we don't have to worry here. And you can determine this via the entropy conservation business by counting degrees of freedom, essentially. So you need the degrees of freedom star in the neutrino, Standard Model neutrino thermal bath at the temperature we're looking at. We divide by G star in the dark sector at the same temperature. And then we also have to calculate these things at the decoupling temperature. So that's first the dark sector at Tx decoupling, divided by G star nu at Tx decoupling to the fourth third. And now you want to have this, small, of course not 10 to the minus 5, but significantly smaller than 1. And kind of our route to tackle this was to make the Standard Model degrees of freedom here at the decoupling temperature as large as possible, meaning we go above the top mass, and then this is 100 something. If you want to be extreme, you can add SUSY, then you have a factor 2 or some more particles at high temperature to make this even larger. But if you say we have the Standard Model, the so Standard Model and plus this dark sector, and then the decoupling temperature much larger than the top mass, then you can plug in things and calculate an effective at an MEV or so when BBN starts. So BBN temperatures, and you find about 0.33, which unfortunately is a bit large these days. I mean, when we wrote the paper, this was, I think, perfectly okay, but today it's a bit much. So that's that. And another way, that's where P1 comes in, is maybe also make this here as large as possible, but then also start adding stuff in the dark sector. Because if you increase the this parameter here, you also increase that parameter, because stuff that's present in the dark sector at low temperature was of course also present in the thermal bath at high temperature. But as this here is a larger number originally, when you add light particles, the ratio becomes smaller, and this way you also suppress delta N. So let's say I have this here under variations. Additional light particles in the dark sector. And yeah, let me just cite Ko and Tang at 1404.236 because I'm running out of time. So that's one variation. Another possibility is that you make your dark photon a bit lighter. I said here MEV scale, because that was the assumption that this decays or becomes non-relativistic before BBN. So we could say this is not an MeV, but 10 keV or so, then it's still relativistic during BBN times. That means here the neutrino, that means here we also increase this this parameter, and delta NF goes down. So dark photon and or dark Higgs. And finally, another funny aspect of this business is that if we introduce these dark neutrinos in the normal way as stereo neutrinos with some mixing with the standard model, with the oscillation anomalies in mind, dark and standard model neutrinos will oscillate. You can, due to these new interactions with the dark photon, you can suppress these oscillations at high temperature, but eventually they will kick in and produce dark neutrinos. That's essentially bad because you will then violate the cosmological bound on the neutrino mass. But it has the interesting effect that you transfer neutrinos from the standard model neutrino bath to the cold stereo neutrino bath. So you kind of lower the neutrino temperature, and this way you can make delta N effective negative. I wanted to mention as one example for a scenario where this is possible, even though it's ruled out, but still, I think it's interesting to know that that you can do that. So let's say oscillations between dark and standard model neutrinos, delta N effective less than 0 is possible. And part of the reason I mentioned is that this was studied in a paper by Tang in 2015 and other groups before and afterwards. So I'll save a bit of time by not writing down the references here. They are in the scans of my notes.
Sorry, one question. In those models, do you assume the relic density at a specific value, or is this a result coming out of the models?
It's a result coming out of the models in the sense that you can calculate it from the mass and gauge coupling in this dark sector. But of course, these things are free parameters, so you fit these parameters essentially to get the correct dark matter relic density.
Okay, and so for what you have been discussing, you basically treat the dark matter relic density as a parameter you can vary. And if I would build a model, then I would have to check whether I can somehow find a parameter point where I get the right relic density, as well as all the masses which you assume here as free parameters as well.
Absolutely. I mean,
okay.
And in fact, I mean, the dark matter relic density goes into here the results essentially that I mean, I'm trying to think what plots we had and where one could see that, but the bottom line is for TeV mass, the self interactions of the right size and the dark matter density as well.
Okay, I see.
And of course, this is then of course, highly model dependent.
Mm-hmm. Okay.
I mean,
Thanks.
Pyongon and Tang had another nice model where there is a non-abelian gauge symmetry in the dark sector that kind of produces dark matter and dark radiation from the same gauge group. Didn't write that down here, but anyway, it's a nice model. And as I'm out of time, let me just I had here another slide. I forgot about motivations for dark radiation. Well, I already mentioned this on Tuesday. Let me also just briefly plug my other old paper where the idea was to produce dark radiation by decays of some other long-lived particle, because that's another way where you can introduce some free streaming of the decay products here and thus lower S8. And yeah, having mentioned that, I mentioned that just recently several people wrote papers on somewhat similar directions with different conclusions. In some cases, the Hubble tension cannot be resolved. In other cases, the S8 tension can be resolved, and then again, some people claim neither of them can be resolved in decaying dark matter models of this kind. I had thought I could talk a bit about these papers in this model building section, but having spent so much time on the CMB, I just leave them for you as references. Maybe if you're interested, you can volunteer me to give a journal club on one of these papers when it's my turn again, or somebody else can pick them up. So might be interesting to look into this.
Excuse me, one question.
Yeah.
In the previous slide,
Uh-huh.
yeah, the last statement by Davari and is this a very robust statement?
Well, no, it's not.
Just for decaying dark matter case, right?
Yeah. It's about this scenario. Dark matter decaying. So a cold dark matter particle decays into a lighter particle which behaves as warm dark matter, and a really light particle which behaves as dark radiation. And so they find, it doesn't work. But I guess that's, as not everybody agrees on that, that means that maybe this is a promising direction to figure it out. And maybe it isn't. I mean, essentially the conclusion so far is that it's really hard to solve both these tensions at the same time.
Okay,
Because it's certainly true that you can push things and alleviate them, but it's not like you go from 5 sigma and 2 or 3 sigma to 1 sigma, but I think you kind of stay in the middle at 2 to 3 sigma overall tension, or at a not very good fit. And so there's not no silver bullet so far that people agree that these tensions are completely resolved. Of course, systematic errors are always popular, but that's boring from the model building perspective. Okay, but then, sorry for the overtime. Let me really go to the conclusions. I tried to tell you a bit about dark radiation and how it influences the universe by changing the expansion rate. I introduced at length this parameter delta N effective that measures how much dark radiation we have here. I showed you the bounds, or quoted the bounds from BBN and the CMB, and the references are somewhere in the notes. And very finally, I wanted to add that in some specific scenarios, you can have other interesting constraints in this direction. So like stuff decaying during BBN, or light dark matter scenarios where you get constraints from here. So this essentially to give you a few more references if you'd like to spend some time reading it on the issue. But I'd better finish now and open for more questions and comments.
Questions? Any question in online? Yes, I have one question about the observing Hubble tension. So, so if we introduce dark radiation, then we have to increase the low lambda, and that, let's say, maybe that means we still need some model to explain the current lambda is bigger than the CMB, or just introducing the dark radiation is enough to.
Well, I haven't really talked about the cosmological constant here, and neither do those models. So kind of the most of the particle physics guys treat lambda as a free parameter of the universe that we don't understand at all, and therefore if you change its value a little bit, that's well, kind of peanuts compared to the 120 orders of magnitude we get this wrong by just estimating from quantum field theory. Of course, there are other people who think about dark energy model building and have not just the cosmological constant, but something more fancy. There, of course, people try to explain the size of the cosmological constant without much success, and they, in such models, you might have to worry about how lambda increases. But I think, I mean, even in quintessence, it's not like you solve this riddle. You again have some model parameters that you can adjust to adjust lambda, and I don't think that this would be a big hurdle in the end. So, but bottom line is, I tend to view lambda as just one input parameter that you can change freely.
I see. Any other questions? If not, let's thank speaker again. Thank you very much.
Thanks everybody for joining, and enjoy your lunch.